Hello everyone, and welcome to the third topic in the SS2 physics curriculum. To those of you who have been part of the video so far, I hope that you've been enjoying what we've been doing here on this channel. And please don't forget that if at any point you have any question at all on your physics or any other subject entirely, you can always drop your questions in any of the comment section, and we promise to attend to all of your questions. Now, this topic is about the equations of uniformly accelerated motion. Now, every student in physics, at least at this level, should have understood what motion is. We've discussed it in our video for SS1 class, where we talked about what motion is, and we even talked about something such as distance, displacement, speed, velocity, and acceleration, amongst other things like that. So you're quite familiar with the preamble to this, okay? But what we want to look at here is there are some three equations that you need to familiarize yourself with if you're going to solve problems on motion, especially the uniformly accelerated kind. Okay, so under this topic, what we'll be looking at, we'll first revisit what we talked about on displacement, speed, velocity, and acceleration. Then afterwards, we then look at the velocity time graph. Now, you have done velocity time graph while you were in SS1. However, this time we'll be going a lot deeper because the velocity time graph you are used to is the one that comes in the shape of a trapezium. Now we'll be looking at other kinds of velocity time graphs, and we'll look at how we can interpret them and get further information from what you get in the graph. Now, after that, we then look at the equations of the uniformly accelerated motion. We're going to derive these equations. I show you how to derive it and how to use them appropriately. And then we'll apply them to solve problems on uniformly accelerated motion. Now, where many students get challenged at this point is they do not know which equation to use as per the question they are given. So I will be showing you some tricks, some tips that you need to have handy when you see a question on uniformly accelerated motion. So that way you'll be able to determine the right equation to solve any kind of problem and how you apply it to get your answer without error. Then after that, we then look at motion under gravity, which is something that comes up from uniformly accelerated motion as well. Now, the difference is this. When we just say uniformly accelerated motion, you are looking at linear motion, which could be horizontal. Now, linear motion does not have to be horizontal. It can also be vertical. So that is why we are looking at motion under gravity. When it moves up and down, it applies the same equation with just slight twist to it. So I'll show you those twists, and then we then apply it in the final stage of the class where we solve problems on motion under gravity. Now, to those of you who are seeing this video for the first time, this is Oya Learn, our channel where we give you helpful educational content. We are always here for you. We are your flawless school too. So ensure that you are subscribed to the channel by clicking the subscribe button. And one thing that can also help you is to hit the notification bell icon so that every time we put out a new content, you will always be notified. And don't forget that we are here for you. If you have any question at all, we are ready to attend to all of your questions. All you need to do is put it in the comment section, and we promise to attend to all of your questions. And please, you can help us to reach many more students who need helpful content like this. Please help us by sharing the video. All you need to do is click the share button. It's not going to cost you a dime. All you need to do is just click the share button and help us to reach many people like you who need helpful videos like this. Now, if you're ready, you can get all your materials, and let's dive into the world of equations of uniformly accelerated motion. And then I show you some of the things you need to know that will help you get ahead in class. Like I mentioned at the beginning of the video, it is one of the things that we have to do before we can dive into equation of uniformly accelerated motion is to revisit displacement, speed, velocity, and acceleration. Now, the reason why we have to do this is because these terms are going to be used as we solve problems on equation of uniformly accelerated motion. So to those who are not familiar with these terms, it is important that you follow the video and understand it fully now. Now, if you want more explanation on this, there's another video where we discuss this at length with examples. You can check that out from the playlist for SS1. It's in the first 10 playlist. You'll definitely find the video where we talked about displacement, speed, and acceleration. Please check out that video and then follow up with what we are doing here. So you don't get lost in all of this, let us look at what displacement is again, what speed is, what velocity is, and what acceleration is. So first we'll define them. So starting with displacement. Displacement. Now you see this term is often confused with distance. But if you check out that video, you see where we explain the difference between them. But if we are asked to define what displacement is we say this is the shortest straight line distance between the start and stop positions of a motion. Now, to get better understanding of this, consider this. If a person were to move from point A to point B like this, point A to point B, you agree with me that there are several ways this person would have moved from here to this point. He could have decided to go on a straight line like this, could have decided to go via a winding road like this, could have decided to go straightward this way and then this way. Now let me show the directions for all this motion. And then this. Now, when you consider all of this, they all involve the motion of an object from point A to point B. But what's the difference between them? If you look at the distance traveled here, it's definitely going to be more than the distance traveled from here to here. And the distance traveled from here all the way through this winding road to this point is definitely more than all of them. Okay? Now, what is the difference between them? Which one is actually the shortest is what determines what you know as displacement. Okay? Displacement does not care the entire length of the path you follow. It's only going to connect your start point to your finish point with a straight line. And the distance of that straight line is what is known as displacement. This is why displacement can be positive, it can be negative, and it can even be zero. Like in the case where you move from point A to point B and then back to point A again. That is from point A to point B and then back to point A again. In this case, it is considered that the object has not left point A, so the displacement would be zero, whereas the distance will be the sum of this length and this length as well. So you see the difference there, right? So back to what we call displacement. The shortest straight line distance between the start and stop position of a motion. Now, let's look at what speed is. When we define speed, we say it is the time rate of distance traveled. This is the time rate of distance traveled. Okay? To put it in simpler terms, we'll just say speed is distance traveled over time taken. So, speed equals distance over time. So, what it basically measures is how fast an object is able to cover a certain distance. Now, you agree with me that some objects cover a distance faster than others, right? So, the rate at which you are able to cover a certain distance determines your own speed. And it will be different from the rate at which another person will cover the same distance. For example, if you were in a race with Usain Bolt and you're running 200 meters, you agree with me that he will cover it faster than you would. I mean, he's the fastest man alive, so he should be able to cover it at a faster rate than you. But if someone were on a motorcycle and was going to cover the same distance, you believe that person would then cover it faster than Usain Bolt, because now he has what? A machine to help him out. So what we are just looking at is what? The time it takes you to cover a distance, and that is what we know as speed. Now, when we talk about velocity, velocity on the other hand is this is the time rate of displacement of an object. Now, they look a bit similar. The difference here is that this talks about what? Distance, while this talks about displacement. And you recall that I told you that displacement and distance, even though sometimes may mean the same thing, they are not always the same. In the sense that distance itself is a scalar quantity, while displacement is what? A vector quantity. It is the distance traveled in a specific direction, which is why we just say the shortest straight line between the start point and the end point of an object. It looks at a specific direction, start to end point, whereas distance looks at the entire path length that the object has covered. So when you consider the entire path length and then you divide that by the time taken, what you are looking at is speed. But when you look at start to finish point and then you divide that by the time taken, then you are looking at what? Velocity at that point. So don't forget, this is scalar, this is vector, which in turn means that displacement will also be what? A vector quantity. And then finally, acceleration. Now, to define acceleration, it is the rate of change of velocity of an object. Let's put that down. This is the rate of change of velocity of an object. We could also replace this with motion, the rate of change of velocity of a motion. Now, that is when an object changes its velocity in the same motion. It starts with an initial velocity, has a final velocity, and then you find the difference between this velocity and divide it by time taken, then you're looking at acceleration. Which is why the equation for acceleration is often written as acceleration A equals final velocity V minus initial velocity U, all divided by time. Let's go over this again. Acceleration is what is denoted here with what? A, the small letter A. Final velocity is what is denoted V. Initial velocity is what is denoted U. And the time taken is denoted here with the letter T. Now, this is how you find the acceleration of an object. Now, all these terms we have talked about here are what we're going to be using when we are trying to derive equation for a uniformly accelerated motion. So just to recap all that we have said so far, displacement is looking at the shortest straight line distance between the start and end point of a motion, while speed is the time rate of distance traveled, that is how fast an object covers a set distance, while velocity is the time rate of displacement of an object, that is how fast an object is able to be displaced from one point to a new point. And then finally, acceleration is the rate of change of velocity of an object. If you do have any question on any of this definition, I will be glad to make a video explaining further. All you need to do is put your question in the comment section. So guys, we already established that velocity is a vector. And you recall from our last videos that whenever you have two vectors acting on an object, they always give us what is known as resultant vector. And we said that that resultant vector is the vector whose magnitude and direction has the same effect as the two vectors acting on the same object. So if velocity is a vector, then everything that applies to other vectors should apply to velocities too. Now, to make you understand this, consider a person who is swimming in flowing river. You agree with me that it is easier to swim in the same direction as the current of that river than when you swim against the current. Now, if you're swimming in the same direction that the river itself is flowing, now what that gives you is that it gives you an added boost. Now, if you recall, when you are working with two vectors that are in the same direction, what do we do to them? The resultant is always the sum of the two vectors. This is why when you flow in the same direction, if you swim rather, in the same direction the river is flowing, you are seen to swim a lot faster than you will normally do. Now, when you do the reverse of this and swim against the current of the river, now the river itself will begin to push you backwards, slowing down how fast you can swim across the river. So what do we see here? It applies to the same thing that happens when two vectors are in opposite direction. The resultant is always the difference between the two individual vectors. Okay, so this is why you see it's easier to swim with the current than you swim against the current. But let's ask ourselves, what then happens when you are swimming in a different direction that is inclined at an angle to the direction of the flow of the river? Now, this is the same thing that happens when you have two vectors that are inclined at each other at an angle theta. Now, you recall that when we discussed this, we talked about solving such kind of problems by applying the parallelogram law of vectors. This same thing applies to velocities. When you have two velocities inclined at an angle, to solve them, to find the resultant, you apply the parallelogram law of velocities. Now, don't get it twisted. It's not something that is way different. It's the same thing. In fact, all you have to do is take the parallelogram law of vectors and then remove the word vectors and replace it with velocities. So let's do that. To state the law of the parallelogram law of velocities, what we'll say is this. Parallelogram law of velocities. Now you see here, in the parallelogram law of vectors, what would have been here is vectors. We've replaced it with velocities. States that if two, now normally what will come is vectors, we replace that with velocities. If two velocities are represented in magnitude and direction by the adjacent sides of a parallelogram, then the diagonal drawn from the point of intersection of the two velocities represent the resultant in both magnitude and direction. So you see, it's a very easy law. All you have to do is remember the parallelogram law of vectors. Then replace the word vectors in there with velocities. Now, you recall that there's an equation for this law, and for vectors, we say r squared equals the first vector squared plus the second vector squared plus 2, the product of the two vectors, then cos the angle of inclination. So the same thing applies here. So instead of using vectors P and Q, we'll then replace them with velocities V1 and V2. And the resultant velocity, instead of using the letter R, we'll just use letter V. So resultant velocity V will therefore, when you square that, will then be equals to what? V1 squared plus V2 squared plus 2V1 V2 cos theta. Now don't forget that this angle here can be the part that can confuse a lot of students. If you recall from that video, I had to show you using a diagram. So let's do the same thing. So let's have a simple parallelogram like this, where this will be our V1 and V2. Now, the resultant V would be the line that we draw like this. This diagonal would be resultant V. Okay, this angle theta here is this one. This angle here that you see that I've shown here is theta. But sometimes when this question is posed, when you are asked as a student to solve resultant velocities, you may not be given this particular angle and instead be given this one here where you have alpha here. If you want to replace it into this equation, you either change this symbol here from plus to the negative sign, that is minus, from addition to subtraction, and then apply alpha here. Or if you want to keep it as plus, then this will now be 180 minus alpha. Okay, it will always give you the same result as theta. So it's quite simple. Don't forget that. You have to be careful which angle you are applying. If it is theta here, just put it straight in this equation. But if it is this one that is given here, which is alpha, you have to either change this to 180 minus alpha, or you change this sign from plus to minus. Now, this is the parallelogram law of velocities. If you have any question, please drop it in the comment section. Another thing that you need to understand a lot more about before you can begin to use the equations of uniformly accelerated motion is the velocity time graph. Now, there are a number of questions you will find where you have a velocity time graph and then you are asked to find either the velocity or asked to find the acceleration of the motion or the displacement, that is the total distance covered by during that motion. Now, this depends on how well you can interpret a velocity time graph. Now, you are familiar with what a velocity time graph is, but for those who are not, a velocity time graph is a graphical representation or a graphical way of describing the motion of an object by plotting the velocity on the vertical axis. Now, vertical axis means your y-axis, and then plotting the time taken on the horizontal or x-axis. Now, what this looks like in most cases is like this. You have your graph where this is your vertical axis or what you know as y-axis, and this is the horizontal axis known as the x-axis. Now remember, it's velocity time graph. So this would show velocity, right? And it is measured in meters per second. And this is time, which is measured in seconds. Now, the common graph usually involves a line that is either inclining like this, could also have something that is linear like this, and could also have what is coming down like this. Okay? Now, that is why we say it's sometimes in the shape of a trapezium. But this is not the only kind of shape you will find when you are drawing the velocity time graph. But it's important we look at this because they show some things that we'll discuss shortly. So let's label this point O. Let's label this point A. Let's label this B. This C. Now I'm going to do something here and call this D. And then I call this E. Now, let's look at what each of these parts of the graph show us or what they tell us. Now, you see OA, line OA here. At this stage of the motion, the object is said to be uniformly accelerated. So this shows uniform acceleration. Now, what do we call uniform acceleration? Now, this is when there is a common change in velocity with time. However small the time interval may be. Now, let me explain this. If an object is changing velocity at the same rate with time, that is, within the first 1 second, the change in velocity is the same as what you will find in the next second. There is a common change in velocity with time. It doesn't increase it or decrease it as the time changes. It's always the same at different time interval. Then what we have there is uniform acceleration. Okay? And the part that shows that on the graph is this part where you have OA. During this time interval, OE, the object is said to be what? Uniformly accelerated. Now, let's look at what AB says. AB shows constant velocity. Okay, now what constant velocity means is that the same displacement is covered in equal time interval. That is, the velocity of the object does not change. It remains the same from time E to time D. So during this time interval, the velocity remains the same. Okay? Whereas in the case of BC, now you see that BC looks a bit like OA. But what's the difference? The velocity at O is 0. But the velocity at A, we can call that V. Okay? Now at B, the velocity remains V. But by the time it gets to C, the velocity has dropped to 0. So this one is reducing, while this one is what? Increasing. So it is called retardation. Retardation. Another name for this is deceleration. That is, the object begins to reduce its velocity gradually at equal interval with time until it comes to a stop. So that's what all of this represents. So now, during time OE, there's what? Uniform acceleration. During time ED, there's constant velocity. And during time DC, there's what? Deceleration, or what we know as retardation. Now, I mentioned that not all velocity time graphs look exactly like this. You can have multiple uniform acceleration shown in the same graph, just as you could have multiple deceleration, just as you could have multiple constant velocity in the same graph. And there are some graphs that do not even show constant velocity at all. We'll still look at different types of this graph, different shapes of this graph. But what is very important that you know is how to find acceleration using this graph, how to find your retardation using this graph, and how to find total distance. Okay? So you see, acceleration is the slope of the graph. Okay? Acceleration is what? Slope of the graph. So if you're asked to find the acceleration of motion at any point of this graph, all you need to do is find the slope of that point. Now let's look at something here. If you are looking for the acceleration between time OE, all you need to find is the slope of this line here. That is final velocity here minus initial velocity, all divided by final time here minus initial time. So, example, during OA, acceleration will be what? V minus 0 over E minus 0. You get that now? Okay? Now, if you try the same thing here, you will see that it will be V minus V, which will give you 0. No matter what the time interval is here, you will still get your final answer to be 0, telling you that there is no acceleration when there is constant velocity. Now, if you apply the same thing here now, what you will get will be a negative answer. Because your final here is 0. 0 minus V will give you negative V. So you always get a negative kind of acceleration during the time that you are looking for deceleration or retardation. Now, when it comes to finding the distance traveled with the velocity time graph, I had mentioned this during the SS1 video of velocity time graph. It is the area of the shape involved. So for example, if you are asked to find the distance traveled during time OE, all you need to do is find the area of this shape, which is a triangle. And you know that the area of a triangle is what? Half base times height. Okay? Now, if you're asked to find the distance traveled between AB here, all you need to do is find the area of this shape here, which looks like a rectangle. And that is basically length times breadth. Okay? But if you're asked to find the total displacement, that is total distance traveled during this motion, then you need to find the area of the entire shape. There are two ways to go about this. You can break it down just as it is here. Find the area of this triangle, the area of this rectangle, the area of this triangle, and then sum it up. Or you just find the area of the entire shape if you can. In this case, it's a trapezium, which is easy. All you need to do is apply half. Okay? Then AB plus ED plus OC, that is this entire length here, all multiplied by what? AE. Or what we just say, half A plus BH, which is the equation for finding the area of a trapezium. You understand that, right? So if you have a simple shape like this, you can find the total distance by applying this equation. Or to just keep it simple, just break it down like this. Find the area of each of the different shapes you can find there. Sum it up at the end, and then you have your total distance traveled. Okay? Now, what we're going to do next is we'll try to solve a question involving this before I then go on to show you other types of shapes you can get from your velocity time graph. In this question here, we are told that a body at rest is given an initial uniform acceleration of 8.0 meter per second squared for 30 seconds, after which the acceleration is reduced to 5 meter per second squared for the next 20 seconds. Now, the body maintains the speed attained for 60 seconds, after which it is brought to rest in 20 seconds. Now, we are to draw the velocity time graph and use the information in the graph to find the maximum velocity attained and the distance traveled in the first 50 seconds. Now, let's solve this step by step, and please pay attention as I'll be showing you some tips that are going to be very helpful for you when you want to solve questions like this. Starting with the velocity time graph, draw the outline of your graph. Now, it is starting at rest, so this is 0. The origin is 0, 0. Okay? Now, during the first acceleration, draw a line to show uniform acceleration, like this. Okay? And then the acceleration reduces. You're then going to do another line like this that bends away from this. Now, at this point, some students think that when they say acceleration reduce, then that should mean that the line should come down like this to show something like a deceleration, but it's not true. Deceleration will only occur when the velocity is reducing. But whenever the word itself there says acceleration, it means velocity is supposed to be increasing. It's just that it's not increasing at the same rate as what you had before. So that's why you see it's bending slightly towards the time taken rather than the velocity. That is, you see that what I mean here is that the slope of this graph is not as steep as what you have here, okay? Because the acceleration is reduced as compared to this, okay? Now that we've gotten that, don't forget that your axes are supposed to be labeled V and then T, which is in time. In seconds here is in meter per second. Good. So after this, it then maintains the velocity. Okay, so we try to draw a straight line at this point. Then deceleration occurs, which brings it to rest. Now, there's something that we need to note here. Time was given. So during the first acceleration, this took place for 30 seconds. So trace this down like this, and then you know what you have here is 30. Now, the next one happened for according to the question, you can see here that it was reduced for what? 20 seconds. So at this point here, only 20 seconds has passed. So when you add 20 to this becomes what? 50. Okay? Now they maintained the velocity attained for 60 seconds. So at this point down, we're going to add 60 to this, which takes it to 110. And then deceleration occurred in 20 seconds. That is, this is 130. Okay? And just like that, we have the velocity time graph. Now you see it has a very interesting shape. It's not a perfect trapezium. We have something here, another slant here before this part, and then this part. So it means that we cannot apply the equation for trapezium when you are looking for total distance. But in this case, we were not even asked to find the total distance. We just need the distance for the first 50 seconds. But before that, we are supposed to find the maximum velocity attained. That is the velocity at this point. Let's call that V2. And then the velocity at this point we will call V1. This one is already known as 0. Okay? And if you recall, I did mention something about acceleration, where I said acceleration is supposed to be what? V minus U over T. Now, what this implies is that V is actually U plus AT. We can apply this to find each of the velocities. So, we need V2, but we first have to find V1. To find V1 will be equal to what? Initial velocity, 0, plus acceleration at this, for this motion here, is 8. Okay? So, 8 multiplied by the time taken, which is 30. Okay? Now, 8 times 3 will give you 24. 24 times 10, and then you have 240. So, 240 meter per second. Okay? Now, V2. V2 will be initial velocity, which is now V1, 240, plus the acceleration for this motion is 5, multiplied by the time for this one is 20, because the difference here is 20. Now, what does this give us? Let's do it once and all. 5 times 20 will give you what? That's 100. 100 plus 240, you have 340 meters per second. And just like that, we have solved the maximum velocity attained. Now, the final part of the question is to find the distance traveled in the first 50 seconds. That is, we need the area of this portion of the graph. Okay, let me show that. This portion of the graph is what we need the area of. So to do this, I'm going to break it down by doing something like this here now. So that you have shape 1, shape 2, shape 3. Now, shape 1 and 2 are triangles, while shape 3 is a rectangle. So let's find the area. Area 1. Now, the area of the first shape is half base times height. So that will be 1 over 2 times, what's the base? The base is 0 to 30, which means we have 30, times the height, V1. V1 is what? 240. So what do we do here? We divide. 2 here 1, 2 here is 120. Okay? Now we have 120 multiplied by 30. Okay? All we have to do is basically say 3 times 12. 3 times 12 is going to give us 36. So we have 0 here, we have 0 here. So 3,600 meters. Just easy like that. Now A2. A2 is also a triangle, half base times height. So 1 over 2 times the base. Here is what? 20, because we have 30 to 50, which the difference is 20. Now the height is just from here to here. Okay? And from here to here is from 240 to 340. And the difference there is 100. Okay? So what do we do? 2 here 1, 2 here 10. So A2 is basically 10 times 100, and that will give us 1,000 meters. And then the final one, A3, which will be length times breadth, since it's a rectangle. The length is what? 240. The breadth is 20. Now, A3 is then what? 2 times 24. That will give us 48. So 0, 0, 4,800 meters. So the total distance for the first 50 seconds is therefore 3,600 meters plus 1,000 meters plus 4,800 meters. Now let's add everything up here. 360010004800. This is 0, 0. Now when you add this, what do you get? That's 14. So 4. Take up the 1. Now this is 4, 5. 5 plus this, that gives us 9. So overall we have what? The distance to be 9,400 meters. Now everything that we have done in this question is able to you can use the same method to find anything at all from this same graph. If you are asked to find the total distance covered in the entire graph, all you need to do is find the area of this one now and the area of this, and then add it to this 9,400, and just like that you've also solved that part. So I believe with this you should be able to solve questions on velocity time graph. However, if you need more examples on this, you can check out our video on velocity time graph from the SS1 playlist. We also solve quite a number of velocity time graph there. So it will help you to gather more knowledge on this. But I believe with this, you should be able to solve any type of velocity time graph. So what I would urge you to do is test yourself. Pick out a question. Try it out using the method that we have used in this question, and then you should be able to get it. But if you come across a challenge while you are solving the question, please drop it in the comment section and we'll be glad to help you overcome such challenge. Many times when students are asked to solve problems on velocity time graph, they immediately go on to draw a velocity time graph in the shape of a trapezium. But I've said this a number of times, that velocity time graph is not about the shape, it's about the motion. So it can take any shape depending on how the motion is. So you are meant to describe the motion, not meant to describe a shape. Okay, so I'll be giving you two types of motion and their velocity time graph, and you see how they are different from the trapezium shaped velocity time graph that we are used to. Firstly, let's consider an object thrown vertically upward. An object thrown vertically upward. Now, what happens when you throw something up? You can pause the video and try it out yourself. Go outside, take an object up, throw it up, and observe how it goes up and then how it comes down. What you are looking at here is the velocity of the object as it goes up and comes down. If you have done this, this should be some of the things you will observe. You see that when you throw the object up, right, it begins to go up but slows down gradually until it comes to a stop. Now that stop is very temporary, meaning it's just for a very small amount of seconds, microseconds sometimes. Okay, then when it stops, then it begins to fall down faster and faster. In fact, the velocity at which it's going to hit your hand or hit the ground is always very large. Okay, so what do you see there? Velocity slows down until it comes to a stop, which is 0, and then begins to increase gradually as it comes down. Now, if you are going to show this on a velocity time graph, what is it going to look like? Now, this is a velocity time graph. Time in seconds, velocity in meters per second. Now, what did we observe? It begins to slow down until it comes to 0. So meaning it starts at a velocity v, which is not 0. It has an initial velocity which is greater than 0. So let's say it starts at this point where velocity is v. Okay? And then it begins to slow down until it comes to 0. What does that mean? Deceleration, right? And how do we draw deceleration? A line that goes this way down. Can you see that now? At this point we have 0. Then what happens next? It begins to accelerate as it's coming down. So acceleration. You see that there is no constant velocity at any point here. What we have is what? Deceleration and then acceleration. This would be the graph that shows what? The motion of an object thrown vertically upward. Every other thing that applies to your velocity time graph also applies to this, in the sense that you can use it to find the distance traveled, you can use it to find acceleration and deceleration of the object. You can even use it to find the maximum height attained. Okay? Now, applying the same thing now, let's look at a different motion. This time, we are looking at what? The motion of a lift. Another word for this, you may be more familiar with elevator. As it moves from one floor to another on a tall building. Now, if you've ever gone to a very tall building before, you have to use the elevator to get from one floor to another. Now, what do you observe when you use the elevator? The moment you click the floor you are headed, what will happen? It begins to speed up gradually. It starts from stop because the elevator has to stop before you can get into it, right? Then from that initial position where it is at zero velocity, it begins to increase gradually. That is, the velocity will what? Increase. Then when it is closer to where it's going to stop, that is the floor you are headed to, it then begins to slow down gradually until it comes to a stop. Now take note, it does not slow down at the middle of the journey. It slows down when it is closer to the end of its journey. So if we are going to draw the velocity time graph to show this motion, this is what it should look like. Remember, this is velocity in meters per second, time in seconds. What happened? From zero, it begins to accelerate. So we show acceleration, which is increasing velocity like this. Now, when it is closer to where it's going to stop, it then begins to slow down until it comes to a stop. Now, you will see that the distance it will travel at this point is smaller compared to this other part. Okay? So this is how you will show the motion of an elevator moving from one floor to another on a tall building. So I hope you understand now that velocity time graph is not limited to that trapezium shape that we are used to. You always have to describe the motion accurately. And all you need is what? Uniform acceleration, constant velocity, and then deceleration. These three things help you to draw a good velocity time graph. All you need to do is understand what happens in the different stages of the motion that you are trying to describe. Whether the object is accelerating and if the acceleration is uniform, or whether it is the same velocity, constant velocity throughout the motion, or whether it is reducing gradually with time, which could be uniform as well. Now, if the velocity is not uniform, what you are going to be having is not going to be a straight line like this, but a curve. Like for example, if you see a velocity time graph like this, what does this show? You see it accelerates uniformly from this point to this point. Then the acceleration is no longer uniform at this point because velocity is still changing. Velocity is still changing, but it's not at the same rate with time anymore. So this would be uniform here, while this is non-uniform. But they are still acceleration. So you see, velocity time graph can take different shape. All you have to do is describe the motion using different lines, whether it's the acceleration, the constant velocity, or retardation. Now, let us look at the equations of uniformly accelerated motion. Don't forget that in these equations, we are using terminology such as displacement, distance, speed, velocity, and acceleration. Okay? So, the first equation of a uniformly accelerated motion is taken from what we define as acceleration. Now, when we defined acceleration earlier, we mentioned that acceleration is change in velocity with time. Okay, where we said acceleration A equals change in velocity v minus u over time t. Now don't forget, what is A again? A is acceleration, v is final velocity, u is initial velocity, and then t is time taken. Now from this we can develop what we know as the first equation of a uniformly accelerated motion. What do? First, cross multiply. A and t comes together to give you at equals v minus u. Now let's make v the subject. V therefore equals, now negative u when it comes here becomes positive, so we write as u, and this is still positive, so plus at. Now this is the first equation of a uniformly accelerated motion. Now we use this to solve questions for objects that have been uniformly accelerated. And when you apply this, you always have to ensure that the parameters here, you have them, and then just one unknown that you are asked to solve for. Meaning you could be asked to solve for the final velocity, or find the initial velocity, or find the acceleration, or find the time. It can't be two from this. It has to be just one of them. The only time where you could have two of these is if you are comparing this equation to something else and then you solve them simultaneously. But if it is not that, you can always apply this if you are asked to find either velocity, final velocity, initial velocity, acceleration, or time, when you have the other ones in this equation given from the question. When you consider the first equation of motion, you see that we have things such as final velocity, initial velocity, acceleration, and time. Now, what if you are asked to find the distance covered or the displacement of the object? Now, you have to use a different equation for this. So let's get an understanding of this. If you are finding the total distance covered, now distance or displacement, distance is supposed to be average velocity multiplied by time taken. Now this is often written as S equals V times T. Now average velocity. What is average velocity? Average velocity is actually final velocity plus initial velocity divided by 2. Let's now put this into this equation and see what we end up with. So S therefore becomes, in place of this, we now have V plus U over 2 multiplied by T. Now, recall, V itself equals U plus AT according to the first equation, right? So instead of V now, we're going to use U plus AT and say S equals U plus AT plus U all over 2 multiplied by T. Let's break this down further. Now, this will mean we have S equals U plus U. That will give you 2U over 2 plus AT over 2 all multiplied by T. Now, if you tidy this up, 2 cancels 2 here. You now have S into what? U multiplied by T. That gives you UT plus, this can be written as half. Then AT times T will give you what? AT squared. Now, this is the second equation of a uniformly accelerated motion. Now, we use this when you are asked to find the distance covered, when you have initial velocity, time taken, and acceleration. You can also use it to find any other parameter that is in this equation. The third and final equation of uniformly accelerated motion was derived from the first and was made to include the total distance covered. Remember, we've already derived the one for total distance, so we said S equals UT plus half AT squared, right? So let's see how we can include that in the first equation without changing anything. Okay, so from the first equation, we have that V equals U plus AT. Okay, now whatever you do to the left hand side of an equation, if you should do the same thing to the right hand side, then you haven't changed anything. The equation still remains valid. So let's square both sides. So that will mean we have V squared equals U plus AT squared. So basically we say U plus AT multiplied by U plus AT. Now let's expand. V squared therefore becomes U squared plus UAT plus UAT plus A squared T squared. Okay? Now, when you add this part together, you get V squared equals U squared plus 2UAT plus A squared T squared. Now, I want to make this a fraction. And what I want to do is to ensure that the numerator is 2. Now, what we have here is 1. 1 written as a fraction can be 1 over 1. It can be 2 over 2, 3 over 3, 4 over 4. All of them still gives you 1. But I want to make sure that I have 2 because 2 is here. So to do that, I will then say V squared equals U squared plus 2UAT plus 2A squared T squared over 2. This part still remains the same. Okay? But from here now, we can now factor out the 2 here. Okay? And then A. I know we can factor T. But if you recall that from the other equation where we talked about distance, it has something with T squared there. So that is why I want to leave this T squared the way it is. Okay? So we can now say V squared equals U squared plus, call out 2, and A. What would that remain? Okay? From here, if you take 2 and A, you'll be left with what? UT. Right? Plus 2 and A out of this, you'll be left with half. Then 1A still remains and T squared remains. Now, does this look familiar? Recall, S is UT plus half AT squared. Okay? Remember I said that it was derived in such a way that we can include what? Distance in the equation that we have here. So if you want to do that now, we just replace all of this with S and say, therefore, V squared equals U squared plus 2A, then all of these become S. This is what we know as the third equation of a uniformly accelerated motion. So let's write the 3 equations and then we can use them to solve questions. So recall the first equation, V equals U plus AT. Second equation, S equals UT plus half AT squared. And then the third one, V squared equals U squared plus 2AS. Now we'll use this to solve a number of questions, but pay attention to the question so that we can then decide how to choose the right equation to solve a problem. So let's do that. Let's consider this question which says, when the brakes are applied to a moving car traveling at 60 kilometers per hour, it decelerates at a uniform rate of 5 meters per second squared. Calculate the time taken to reach a velocity of 36 kilometers per hour. Now let's look at what we have. Now, what are we given in the question? The initial velocity, U, is 60 kilometers per hour. Okay? Now, what does this mean? You have to convert it into your the proper SI unit. Remember, this is kilometer per hour, and the SI unit for velocity should be in meter per second. Now, to do this, what do we say? Now, kilometer means 1,000, so 60 times 1,000, all divided by 1 hour. That is what? 60 seconds times 60 minutes. Now, let's see. This will be in meter per second, right? So 60 here takes out 60. So U therefore becomes, if 0 goes here, that's 100 divided by 6, which is basically 50 over 3 meters per second. Now, let's do the same thing to the final velocity that we are given. The final velocity is 36 km per hour. V equals 36 km per hour, which will mean we have 36 times 1,000 all over 60 times 60. Okay? Now, what do we have here? This would mean 36 times 1,000 all over 3,600. Okay? 0 cancels 0, 0 cancels 0, 36, 36. We are left with 10 meter per second. Now, that's for U and V. What else are we given in this question? Okay, we can see we have a uniform rate of deceleration. Now, here's something you should bear in mind. Deceleration is negative acceleration. So if we are going to denote this as acceleration, then it will take a negative sign. It will now be minus 5 meter per second squared. And then we are asked to find T, time. Okay, so we have U, V, A, and we need T. So which equations has U, V, A, and T? That is equation 1. Okay, so that means the right equation to use to solve this is V equals U plus AT. So if we apply V equals U plus AT, what are we going to get? V is what? 10 equals U, which is what? 50 over 3 plus A minus 5, then T. So what this implies is that 10 equals 50 over 3 minus 5T. Let's make this a straight line equation by multiplying through by 3. When you multiply through by 3, you have 30 equals 50 minus 15T. So from here now, we can then say 15T equals 50 minus 30. So 15T equals 20. Now this implies that time T equals 20 over 15. Okay? Now from here, what do we see? 5 goes here 3 times. 5 goes here 4 times. 4 over 3 will give you 1.33. And it is in seconds. So the time taken is 1.33 seconds. And that's the solution to this question. Now let's solve this question where a body moving with an initial velocity of 30 meters per second accelerates uniformly at a rate of 10 meters per second squared until it attains a velocity of 50 meters per second. Now we are asked to find what the distance covered during this period is. Okay? Now, to solve this question, what you have to do first, speak out what you have from the question, that is the parameters you are given. Then when you have those, you then decide which equation of motion you're going to use to solve it, and then you go on and apply it. So you can pause the video, do that yourself first, and then compare what you have done to what is done in this video just to see how well you do it. And leave us a comment if you got it correctly. Now, let's solve it together now. Ensure that you compare this with what you have done. The first thing is to state what we have. So we are given that the body has an initial velocity u, which is 30 meters per second, and it is in the correct SI unit, so we leave it as that. Now it accelerates uniformly at, so acceleration is given a 10 meters per second squared. Okay, and then it attains a final velocity of 50 meters per second, so v is 50 meters per second, and we're asked to find the distance. Now, which equation involves U, A, V, and S? It should not involve any other thing apart from these four. Okay, so we see that the right equation to apply here would be equation 3. V squared equals U squared plus 2AS. So we're going to apply that. V squared equals U squared plus 2AS. Now, let's solve it. What is V? V is 50. So that will be 50 squared equals U, which is 30. So 30, so since it's U squared, we square this as well. Plus 2 multiplied by A, which is 10. All of this multiplied by S. Now, what is 50 squared? That will give you 2500. Okay? Equals 900 plus, this is 20S. Now, make that the subject. 20S therefore becomes 2500 minus 900, which will give you 1600. Okay? So, if 20S equals 1600, we divide both sides by 20. Now, what does this give us? It implies that S, which is the distance covered during this period, will be what? 0 cancels 0. Now, 2 in 160 will give you 80. And it is measured in meters. So, the solution to this question is that the distance covered during the period is 80 meters. Here is another question, and it says a car accelerates uniformly at a rate of 10 meters per second squared from an initial velocity of 36 kilometers per hour for 30 seconds. Now, find the distance covered in this period. Now, you can pause the video, try this out yourself, and then compare your answer to what is gotten at the end of this video. Good luck. Now that you've solved it, let's see what you got compared to what we are going to get at the end of this video. So let's do this. Solution. What are we given? We're given that it accelerates uniformly at 10 meters per second squared. So acceleration is 10 meters per second squared. Okay? Now, we are also given that the initial velocity is 36 kilometers per hour. Initial, that is U. And that is 36 kilometers per hour, which, if we're going to convert this into meter per second, would be 36 times 1000 all divided by 3600, which is 1 hour in seconds, and this is meter per seconds. So 0 cancels 0, 0 cancels 0, 36 cancels 36. That means U is therefore what? 10 meters per second. So we have our initial velocity now, and the time taken for this T is 30 seconds. Okay? And that's all that we have. So we are then asked to find distance. Now, which equation of motion involves acceleration, initial velocity, time, and distance? You see that is equation 2. Okay? And distance is already the subject there, so it's quite easy to apply. So to apply that, we're applying S equals UT plus half AT squared. So let's see what we get. U, that is 10, multiplied by T, which is 30, okay, plus half. A is what? 10, multiplied by T squared, that is 30 squared. Now, what are we going to get from this? So S therefore becomes, when you multiply this, you get 300 plus, now what do we have here? Half of, okay, let's keep the 10. So we say half times 10 times, what do we have here? This would give us 900. So we can easily break this and say S equals 300 plus 2 here 1, 2 here, that will give us 450. Okay? And 450 times 10 will give us 4,500. Now, when you add all of this, S therefore becomes 4,800 meters. or you just put it as 4.8 kilometers. Any of these two is correct. Now, I would like to sound this. Whenever you are solving questions like this, you are not mandated to leave it at a particular unit, except when you are dealing with a multiple choice question. Now, for example, it's a multiple choice question, and from the options provided, I can't find 4,800 meters, but the options are rather in kilometers. That means I'll pick the one that is 4.8 kilometers. Now, sometimes it may not be exactly what you have, but might be an approximate value of it. For example, if what I'm having are whole numbers, the closest whole number is what I'll pick, which will be 5 kilometers. I hope you understand what I mean here. Okay, so it means that you are at liberty to choose which one is closest to your answer when you are dealing with multiple choice question. Okay, but when it is not multiple choice question, you can leave it either like this or like this, and it will still be marked correctly. If they want you to leave it in a particular unit, it will be stated, leave your answer in kilometers to 1 decimal place, to 2 decimal place, and so on like that. So when those are specified, then you have to follow the specification you are given. Otherwise, feel free to leave your answer whichever way you please. I hope this has helped you. Now, when we are looking at objects that are uniformly accelerated, they don't always go along the horizontal path. Sometimes they could also be vertical path. That is, the motion could be when it is moving upwards or downwards. So those kind of objects are said to fall freely under gravity. Like when you throw a stone vertically upward, it goes up, slows down, stops, and then falls back down. The same thing applies to every other object that you throw up. They will always go up and then fall down freely under gravity. And the same equation that you use to solve a linear motion of an object that is uniformly accelerated is the same thing you will use for motion of objects falling freely under gravity. There's only a slight twist to it. Okay? So for motion under gravity, for example, distance S becomes h, where h is what? Height. Okay? That is vertical height above ground. Another thing that changes is that acceleration A becomes g, which is what? Gravitational acceleration, which is an acceleration due to the effect of gravitational pull of the earth. Okay, now these two will come into the equation. Then there's another thing, which means that depending on the direction the object is moving, you could change sign. Like when the object is moving upward, it is moving against gravity. Gravity is supposed to pull it down while it is going up, so they are in opposite direction. We use negative sign there. But when it is in the same direction as gravity, that it is falling towards the ground, then it takes the plus sign. So this gives us equation from, now what you know as V equals U plus AT will now become V equals U plus or minus GT. Okay? Now the plus will be used when the object is falling down to the ground, and minus will be used when it is rising above the ground. I hope you understand what that is, right? So G is introduced here, and then the plus or minus. Now the second equation, which you know as S equals UT plus half AT squared, will now become, instead of S, we would have H, which is vertical height, equals UT plus or minus half GT squared. So you see, we introduce vertical height here, and G also comes in with the plus or minus. Don't forget, plus means the object is coming to the ground, minus means the object is rising above ground. And then finally, the third equation, which is known as V squared equals U squared plus 2AS, will now become Okay, it becomes v squared equals u squared plus or minus 2gh. Okay, now we use this equation when you are dealing with objects moving freely under gravity, but there are some things that may not be told in the question. Remember, when you are dealing with the linear motion, you are always given initial velocity, final velocity, amongst other things. There are some questions you will find where some information will not be stated directly. Okay, like for example, an object that was thrown vertically upward and allowed to fall freely under gravity will get to a point where at its maximum height, what happens to that object? At that maximum height, the object will stop temporarily before it falls back to the ground. Remember when we talked about something like that, right? So at that point, velocity becomes what? 0. So if you are considering the motion upward, initial velocity is whatever velocity you give to it when you throw it up, while the final velocity will be 0. But if we are considering an object that is falling freely under gravity, initial velocity is then 0, while final velocity is the one before it hits the ground, which is v. In that case, you can then calculate that value. Okay, so you always have to understand how is the object moving so that you can know what to use as initial velocity and what to use as final velocity, and to also know whether you're using the plus sign or the minus sign. Now, another thing you should also know about this kind of equations is that the value of g is not a constant figure. Okay? Now, on Earth, gravitational acceleration ranges from 9.8 till about 10.2, depending on your location on Earth. You see, at the equator, it is 9.87 thereabout. Okay, and nations that are around the or close to the equator have similar value for gravitational acceleration. This is why we say Earth's gravitational acceleration is approximately 9.87. Okay, but it changes as you move away from the equator. Some places it is as high as 10.1, 10.2 meter per second squared. At some places you find it at 9.9. Okay, so when you are solving a question in physics and you are not given the value of gravitational acceleration, it is safe to use an approximate value, which is 9.87. Okay, but when you are given a value to use, stick to that. Now, most times for students in the senior secondary level, we often give them a value of 10.0 to use for gravitational acceleration. So always look out for that. You'll be told, given that g is, so if you are given the value of g, use that value. But when you are not given, use 9.87 meters per second squared. Okay? Now that we have discussed this equation, let's apply it to some question and see how you can solve for final velocity, initial velocity, gravitational acceleration, time, or even height above ground. This question says, a cricket ball is thrown vertically upward with an initial velocity of 40 meters per second. Now we are asked to find its velocity after 3 seconds and then the maximum height attained and the time taken to reach this height. Okay, now when you look at this question, you see that the object is thrown vertically up. That is, we are looking at motion under gravity. So let's see how we solve it. Okay, now from the question, we are given some things. Okay, we have that the initial velocity, so that is u, is 40 meters per second. Okay, now we want to find the velocity after 3 seconds. Now, to make this simple, I am going to take g as 10 meters per second squared. Now, recall that I mentioned that the question will always tell you what to use for g. It could be 10 like this, it could be another value entirely. Okay, I'm using this value because it's easier to solve questions with the number 10 in them. Okay, so now that we have this, we take our g also as 10 meters per second squared. Okay, we are asked to find the final velocity v after time t equals 3 seconds. Okay, this is for the A part. So let's apply it. The equation to apply here would be V equals U. Now remember the object is going up, so minus GT. Okay, so V therefore becomes 40 minus G, which is what? 10, times T, which is 3. Now what does this gives us? Now we have V as, this will now be what? 40 minus 30. And our answer is 10 meters per second. That is the final velocity after 3 seconds. Now we can go to the B part. The B part says we should find the maximum height attained. Okay? So to find this maximum height, h, consider that maximum height, velocity will become 0. Okay? So at max height, V equals 0. So we can apply V squared equals U squared. It's going up, so minus 2AS. 2GH, I mean. This is motion under gravity. So A becomes G and S becomes H. Good. So since this is 0, V squared will also be 0. So we can then say 2GH equals U squared, which implies that the maximum height H will be U squared over 2G. So what is U? U is 40. So 40 squared divided by 2 times 10. Okay? So H therefore becomes 40 squared will give us 1600. Divided by 2 times 10, that's 20. 0 cancels 0. This will give you 80 meters. That's the height that it will get to, the maximum height. Now, we are also asked to find the time it will take to get there. So, taking V as 0, we can still apply V equals U now. Okay, minus GT, which means that GT equals U, since V is 0. Okay, so from here we can say the time T equals U over G. And U is what? 40. Divided by G, which is 10, and we'll get what? 4 seconds. So the time it will take to get to its maximum height is 4 seconds. So you see now that every second, the velocity is increasing by 10. Okay, since at 3 seconds we get 10 meters per second. And at 4 seconds it becomes 0. It's quite easy to understand this type of motion. So you can apply this same method to other questions on motion under gravity. But let's look at another question before we go on. Here is another question to practice with when solving questions on motion under gravity. Now, in this question, we are told that a ball is projected vertically upward from the top of a tower 60 meters high with a velocity of 30 meters per second. And we are asked to find the maximum height above ground. So let's solve. Don't forget, the first thing you want to do in this case is to note what you have here. So, initial height above ground, H1, is given as 60 meters here. Because the object did not start from the horizontal ground level. It started at a height of 60 meters. So let's note that. Okay? Now, we need to find H2, which is the height, the maximum height an object is supposed to reach when you project it vertically upward. Okay, since we have this now, we now know that the maximum height above ground, H, will be H1 plus H2. Okay? Now, what other thing do we have here? We have initial velocity U as 30 meters per second. Okay? Now, let's take G as 10 meters per second squared, also in this question. Now, I'm saying this again. I'm using this value because it's easier to work with this value, okay? When you are asked to solve a question on this, take note, you will be given the value of G to use. I'm only using 10 to make the calculation a lot more easier here. Okay? So what equation do we apply in this case? You must note that at max height, at maximum height, final velocity v ought to be 0. Okay? So since we have v, we have u, we have g, and we need h, the equation we use in this case is v squared equals u squared. Now it's going up, so minus 2gh. Now v is 0, so 0 squared equals u squared. U squared, that will be what? 30 squared minus 2 times 10 all multiplied by h. So from here we can just say 2 times 10, that's 20, minus 20 coming here becomes plus. So 20h equals 30 squared, which is 900. That is, to get h, we divide both sides by 20. Now this h we are solving here is actually the h2 in this case, okay? So 20 cancels 20, so h2 here becomes 0 here. So what we have is what? 45 meters. So the height above ground, which is what we are asked to find, will now be 60 meters plus 45 meters. And when you add this, you get 105 meters. And that's the solution to this question. Now, folks, I'd like to urge you to practice with even more questions on motion under gravity. And you can try out questions from the WAEC exams, the JAMB exams, and so on. Try them out, apply the principles we've taught in this video. And if you come across any challenging question and would like some help with it, kindly put it in the comment section and we'll definitely attend to all of your comments. And folks, if you're yet to be subscribed to the channel, this will be the time for you to take a moment and click the subscribe button. It doesn't cost you a dime. Just click the subscribe button and you become a part of this wonderful family. You can also hit the notification bell icon so that every time we put out a new video, you will also be notified. And we are also urging you to help us reach many more students like you who need helpful videos like this. Now, the way you can help us is to share this video. So please, before you leave, ensure that you click the share button so that we can reach many more students like you who need helpful content like this. So let me tell you a big thank you for following the video so far. There's still more to come in SS2 physics curriculum, and I'll be seeing you in the next video. Bye for now.